Last name. All right. Hello, everyone. How are we doing? Are we having a good time? Do we guys got plans for the weekend? Because you know it's like your last weekend, right? Because this weekend right here, and then the next one you guys study for a whole bunch of tests that's coming, and then you guys study for the final exams. So this is like your last weekend, right? Or you guys just recognizing that now? Mm, And then all of a sudden the summer hits, and then you're off to make $1 million. And no, no, all right, bro. Hopefully, you guys do make $1 million, and then you come back and you share some with me. You say, "It's because of you I made this $1 million. Here is $500,000." You know, just only half is what you're saying. Yeah, I agree. It should be higher. I agree. I, I do agree. I do agree. All right. So again, we are in 8.1 Introduction to Statistics right here. And then what we talked about were your null and your alternate hypotheses, right? The basic idea right here is we have two possibilities, and one of them we consider to be innocent, i.e., the null hypothesis, i.e., the long run, quote unquote, truth, right? We've been given this statistics class now for 50 years. The average for this class has been 75 for 50 years, right? So I'm going to say, hey, I'm going to make a new way to teach this class. Yeah. Right. And because I come back and after I take my average of my students and I come back with an average of 78, right? We need stronger evidence than that to state that, you know what, you might be right. This method is better than what we've been doing in the past, right? The main issue right here is what we call random chance. Because I did something different, it just could be a lucky chance that my group of students happen to be better. And that's why the score is better, right? Or the drivers we selected for the particulate matter coming out of the car, the drivers just be easier. They weren't as aggressive as normal drivers would be. And that will account for the outcomes that we see. All right. And so these things right here, they work as what we call a trial. We assume that the null is true. We look for evidence, and then we make a decision on the null. Either we accept the null or we reject the null. The problem here is that we need to have really strong evidence before we can reject the null hypothesis. All right, questions there. And so that's what we're kind of going to look into today. But before we do that, one last thing that we need to come right here. Again, so stating our conclusions, we state one of two things. Either the null hypothesis is not rejected, right? Again, we're just going to simply say there's not enough evidence to conclude that the alternate hypothesis is true. Uh, or on the other hand, the null hypothesis is rejected. Again, the conclusion is that the alternate hypothesis is true, right? Notice in the language, we never say the null hypothesis is true, right? Because often we come back with only a 20% chance the null is true, although we're sticking with it, right? And so that's why we have these statements right here. And so we could do a little bit of practice right here. Boxes are certain kind of cereal are labeled as containing 20 ounces. An inspector thinks that the mean weight may be less than this, and so he performs this test right here. Null hypothesis that the mean weight is 20, alternative hypothesis that the mean is less than 20. And then after he gets his data, he rejects the null hypothesis, right? So state the appropriate conclusion. The appropriate conclusion will be that the alternate hypothesis is true. Of course, this is English, and so we have to write this right here. We conclude that the mean weight of cereal is less than 20 ounces. All right? Questions there. So in other words, we're just changing this statement into English. Questions there. Again, remember mu represents the mean weight of cereal. Questions there. Let's rerun this thing right here, but let's say he didn't get enough evidence to support the alternative hypothesis. And so in other words, we're going to stick with the null hypothesis. And so this is how we state the equation. We don't say that the mean weight is 20. Instead, we say there is not enough evidence to conclude the alternative hypothesis is true. Questions there? When the alternative is true, we can say, yes, the alternative is true. When alternative is not true, we can't simply say that we don't say the null is true. Questions there? On the language. Because you know how it is when you do the homework, they have them multiple choice questions for like 50 words. And you guys squint through them, which words are different. We're trying to figure out which is the right one, yes? Yeah. You guys don't enjoy doing your homework? You don't make your homework into a little game? No, you guys just say, I hate doing this and click away. I hate doing this and click away. Why am I doing this? Click away. Is that how you do your homework? Y'all need to work on that thing. Y'all need to work on that. Happiness and joy. Oh, click. Oh my goodness, right? All right, again, another way to say this right here, there is insufficient evidence to conclude that the mean weight of cereal boxes is less than 20 ounces. Questions there? Yeah, cool. So that's the end of this section. Let's go into 8.1 almost. Please, I'm speaking to the choir. All right, so let's move into our error types. Because there are two possibilities, right? Either the null hypothesis is accepted or the alternate hypothesis accepted. It turns out that means there are actually going to be two types of errors that we can make. The first type of error is called a type 1 error. I'm just great at naming stuff. No. A type 1 error occurs when we reject the null when we should not. A type 1 error, because remember, the first goal basically is the null, because normally the null is true, yes? It's normally we accept the null. So a type 1 error is we're moving down to the alternate hypothesis when we should have stuck with the null hypothesis, right? That's your type 1 error. A type 2 error is the reverse of this process when the null is false, but we fail to reject the null. In other words, the alternate hypothesis is true, but we still stuck with the null hypothesis. We call that a type 2 error. Okay? So a type 1 error, we should give an answer of null, but we're saying alternate. A type 2 is we should say the alternate is true, but instead we're sticking the null. All right? Questions there? Normally, the way I try to get myself to remember it is just remember what type 1 is. A type 1 is, I should have stuck with the null, but I rejected it. That's your type 1 error. Okay? Type 2 error is going to be there for the reverse. I should have picked an alternative, but I did not. All right? Questions there. Here's a little picture right here. By the way, if you should reject the null and you do, you made the correct decision. If you should fail to reject the null and you do that, that's the correct decision, right? An error is made when you're doing the wrong thing. And that's why there are two types of errors right here. So watch carefully. The null is true, correct? But I'm going to reject it in error. This is a type 1 error. The null is where we should be. I should come back and say, yo, you don't have enough evidence to go with the alternate. We should be going with the null. But then you say, no, I'm rejecting the null. That's the type 1 error. A type 2 error, on the other hand, right here, is the null is incorrect. You got enough evidence, yo, go to the alternate, but you still say, no, 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 we're going to stick with the null right here. That's a type 2 error. Questions there? Because, I'm about to ask you questions about these two errors. Questions there? Questions there? All right, cool. So let's try them out right here. The dean of a business school wants to determine whether the mean starting salary for graduates at her school is greater than $50,000. She will perform a hypothesis test with the following null and alternative hypothesis. Mu is equal to 50. Alternative, mu is greater than $50,000. Suppose that the true mean is 50,000, i.e. HO is the correct answer. Yes? So if she makes a correct decision, she will choose the null hypothesis. Yes? And the dean rejects the null hypothesis. Oh no. Is this a type 1 error? Is this a type 2 error? Or is this the correct decision? All right, we're going to do this by show of hands. Show of hands. Show of hands. I'm going to ask you 3 questions, and you show your hands when you think I'm asking the right one. All right? You have to raise your hand for something. All those things are type 1 error. Don't look around. Don't look around. All those things are type 2 error. All those think this is the correct decision. Who didn't vote? The correct answer, it is a type 1 error. The null, that's true. The null is true, but we are rejecting the null. This is a type 1 error. We're stepping on the poor null. We should not. He should be cradled until he's okay. He's right. Questions there? Questions there? All right, try again. Same scenario right here. But let's say that the true mean salary is now $55,000. And again, the dean rejects the null hypothesis. Is this type 1, type 2, correct decision? Go ahead and lock in your answer. Everybody's locked in their answers? So you're not going to look around? Is this a type 1 error? Is this a type 2 error? Is this the correct decision? The correct answer is that this is the correct decision. Does that make sense, or you still have a question? Remember, the true mean is 55,000. Isn't 55,000 greater than 50,000? Doesn't this mean that these two, doesn't that mean that these two things are aligned? I.e. is true, the alternative is true. Therefore, I should reject the null, yes? And so therefore, it is the correct decision. All right, last one. Again, same scenario right here. Suppose the true mean again is $55,000, but this time the dean fails to reject the null. Go ahead and make up your mind. Lock in your answer. All right, is it a type 1 error? Is it a type 2 error? Is it the correct decision? Get above one of them. And the answer is, it is a type 2 error. Again, just like a while ago, this is saying the alternative is hypothesis is true, right? The alternative is claiming that the mean is greater than 50,000. Isn't 55,000 greater than 50,000? So in other words, this is true. But guess what? She's saying, I'm going the other way. I'm going with this one. That's an error, yes? That's a type 2 error. Questions about either of them, correct decision, type 1 error, or type 2 error? That a no, I'm saying no questions? Cool. All right, so that takes us into creating and running hypothesis tests for a population where the population where sigma is known. So if you recall from the previous section, we did 7.1, 7.2, and 7.3, yes? 7.1 was when sigma was known, and we used the Z distribution, yes? 7.2 when sigma was unknown, and we used the T distribution, the student T distribution, yes? Same process is happening here. So we're in 8.1, we're going to be using the Z distribution. In 8.2, we're going to be going into the T distribution. And in 8.3, we're going to run the hypothesis test for the proportions. Questions there? The nice thing about the hypothesis test is that they're pretty easy to run because basically it's the same button clicks that we did for the student T distribution, right? The difference is the difference is you have click hypothesis test instead of confidence interval. Pretty straightforward. All right, so let's roll. Again, we have the same exact 4 assumptions we had the last time, right? Sigma is known. We have a simple random sample, and we have a question on the population size. If the underlying population is normal, any size will do. If the underlying population is not normal, then for the central limit theorem to hold the CLT, n must be greater than or equal to 30. But again, these two are actually the same process right here, is that we just need a large enough sample size. And they're telling you how to determine that. Questions there? Again, the next section, 8.2, this is going to be sigma is unknown. That's the main difference right there. There are 2 ways to perform a hypothesis test. There is a critical value method, and then there's the p-value method. We're going to actually do it in reverse to how they did it right here, because the p-value method is actually the standard method. If you go read any of them fancy papers that they have out there in the world, they will quote things by the p-value as opposed to the critical value method. I do need to show you how to calculate your test statistic. It is your Z score for excuse me for your based upon your data that you collected, and then we'll go ahead and we'll work on them from there. So all right, the College Board reported that the mean for the math SAT score in 2009 was 515 with a standard deviation of 116 points. Results from earlier studies suggest that code students should have an SAT score of approximately 530. Yes? A teacher who runs an online coaching program thinks that her coach students will have a higher average score. Can you tell me what the null and the alternative hypothesis is going to be for this right here? Anybody? Anybody? Don't you all raise your hand at the same time? Anybody? Going once? Yes. Mu will equal 530, because we're talking about coach students. And then the alternative hypothesis would be the mean would be greater than 530. This will be a right-tailed test. Yes? So that's your null right here and your alternative right here. will be the mu is greater than 530. In other words, the 515 was a ruse, yes? The 515, because we're talking about coach students. So therefore, coach students will generally do better already. But they say she's even a better coach. So she's comparing against the 530 number. Questions there? Questions there? All right. And you guys remember how to find a Z value, a Z score? Do I remember how to show you how to get insult? Okay, I do. All right, I do. All right. So again, your test statistic is simply the Z score for your data value. So right here, suppose that the teacher draws a random sample of 100 students who are planning to take the SAT and enrolls them in her online program. After completing the program, their sample SAT score is now 562. So first things first, is 562 greater than 530? Yes, right? So this is giving us some kind of evidence that the teacher is doing better than the average coach program, because the average coach program would be 530. Yes? The real question, though, is this strong evidence or not? That's the real question right here. Is this strong evidence or not? All right. And so the test statistic is simply the z-score. I will remind you how to find the z-score in SALT in just a little bit right here. But basically, you plug in the values in here, and that gives us an answer of 2.76. This right here is your test statistic. Question there. I'll show you how to do this in a second. All right, so I'm going to skip ahead in the program, right? We're going to skip ahead in the program and we're going to get into the next slide. And I'll come back in a second. 1, 2, 3. Ah, I hit the wrong one. Sorry. Boom, there we go. And what we're going to go to is the p-value method. We're going to go to the p-value method. I like to think of the p, now it's not exactly correct, but I like to think of the p-value method, excuse me, as the probability that the mean is true, or the probability that the null hypothesis is true, to be more precise. It's not exactly true, but I like to think of it as the probability that the null hypothesis is true. Okay? And so basically, again, the p-value right here tells us how unlikely or how unusual the test statistic is, right? And so because of this right here, this is basically saying the smaller the p-value, the stronger the evidence against the null hypothesis. The smaller the probability that the null hypothesis is true, that's more evidence against the null hypothesis. Does that kind of make sense to you? Does that kind of make sense to you? Your p-value right here, probability, right? The smaller number. Imagine this scenario right here. There's an 80% chance that the null hypothesis is true. Is that strong evidence against the null? But imagine instead, I had a 1% chance that the null hypothesis is true. That is strong evidence against the null. Yes? 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 And so the p-value is simply calculate that probability, and then you use that to make a judgment about the null hypothesis. Questions there? So that therefore makes sense that the smaller the p-value, the stronger the evidence against the null. That makes sense? No? Maybe? Kind of? Sort of? Oh, fine then. Fine then. All right, so we're looking at the same question right here. And the question is, how do I calculate the p-value? So let me remind us, the null hypothesis is 530, right? The long running, it has been that the average coach student score is 530. This new lady, this new teacher says her students will do better. So she got 100 students to take the SAT and they scored a score of 562. So far, so good? Yeah? And again, we know that the standard deviation for the test is 116 points right here. And so now let's go ahead and run our p-value test in SALT. Questions there before we try the test? All right, cool. So Is there a way I can have both of these things open at the same time? The answer is yes and no. So let me do this right here. Let me see if I can show off a little bit. Uh, where is my good friend Salt? Hello, Salt. We missed you, but we're back. Just a little bit. All right, hopefully you guys can see the numbers over here. All right, so again, basically in salt, what we're going to do right here is we're going to go into our distribution calculators. Again, we're actually going back old school because everything that we're doing here right here is going to be basically what we've always done before. So first things first, we got to put the mean and the standard deviation. What's the mean for the data set right here? The mean is 530. So I'm going to put a mean right here of 530 right here. What's going to be the standard deviation right here for the data set? The standard deviation is going to be not 116. It's going to be 116 divided by the square root of n. Do you remember that when you have group data, when we're looking at means instead of just x right here? Remember that's how we started 7.1? No, that's how we ended 6.4, 6.5, right? Because it's group data, we don't just stick the standard deviation, we gotta make it smaller. We gotta divide by the square root of n, yes? What's the square root of 100? And so we're going to be dividing by 10. So I'm going to put in here 11.6. Just like I said the last time, this is the area where students get these things wrong, is they have the wrong standard deviation. Everybody understand why I am going 116 divided by the square root of 100. Everything else falls in line right here. So this right here is a greater than. So is this a right tail test or a left tail test? Right tail test. So I go over here and I click on a right tail. Notice it switches over to the right side for us. Our error is on the right side. Yes, sir. Yes, sir. And then what score did our friends get on the test? Our 100 students. What's the average score for the 100 students? 562. Yes, sir. Yes, sir. Yes, sir. Yes, sir. So there are two numbers in here that are important. By the way, they have the region shared for us over here. There are two numbers that are here important. This score right here, the probability, p-value, the probability, the p-value are the same thing. Your p-value for this data set is 0.0029. The probability that the mean is true, again, it's not exactly correct, but the probability that the mean is true is 0.0029%. That is a really, really small chance that the mean is true. Yeah? 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 And remember, I showed you going to show how to calculate the test statistic. This score down here is your test statistic. Questions there? Just because remember, your test statistic is a z-score, 2.7581. If I come over here on my picture, right here, you see the z-scores down here, 0, 1, 2, 3. See, it's between 2 and 3. Yes? 2.7 is closer to the 3. That's why this right here is your z-score. Question, sir? So now that we know the p-value, how do we make a decision? Am I going to reject the null or am I going to fail to reject the null? Let's go ahead and show you how that last process works right here. All right, so again, like they were just saying right here, or like I was saying, right? We're going to run the p-value test right here. To run the p-value test right here, I need to know that the mean is 530. The standard deviation, notice how they put the numbers together in this example. Can I help remind you? It's 116 divided by the square root of n. That's your standard deviation. And you plug in probability x is greater than or equal to 562. And that pumped out a probability number and that was our p-value. All right. So now here is the magic part right here. So again, we did all of this already. We got our p-value of 0.029, 0.0029. So right here, that's our p-value. Again, P just stands for probability in my head because it's the same thing within chapter 6. Chapter 6 says find the probability, plug all the numbers into solve, and you took them in that box. That's your p-value. Questions, sir? Questions, sir? And so then, here we go. There is a simple rule that we follow right here. And that rule right here is we have to create an outside number called alpha. We have to create an outside number called alpha. Alpha is our tolerance level, or the level at which we make the decision to switch from the null hypothesis to the alternate hypothesis. The basic rule right here is that alpha should be small, and that the smaller the value of alpha, the stronger the evidence we need to reject the null hypothesis. Right? Remember we talked about this last time? Let's say we have an 80% chance, a p-value of 80%. Should I reject the null, or should I stick with the null? Most likely, I will stick with the null, right? So let's say I have a p-value of 0.8. Most likely, I'll stick with the null, yes? If I have a p-value of 0.5, 50%, I will still stick with the null. If I have a p-value of 0.2, I will still stick with the null. The general standard that we use is 5%. Normally, we set alpha to be 5%. And so the rule is, if the p-value is smaller than 5%, you reject the null. So in other words, if there is less than a 5% or less chance that the null is true, that's when we start gravitating away from the null hypothesis. All right. Anything else? 6%, 7%, 8%, 9%, 10%, 28%, 80%, anything else, we go with the null hypothesis. We fail to reject the null hypothesis. Questions there? Questions there? 5% is the normal cutoff mark. Again, normally when you're doing these research, you do this before you even started. You're going to say, hey, look at history or whatever. We're going to go for alpha level 5%. Because obviously you can change alpha level after you've done this, I'm just going to make my alpha 80%. Yes, right? So no, normally we set the alpha before we start the experiment, and we use some kind of standard before we get started on that alpha level. All right? Like, for example, you can just choose the standard of 5%. And then you run your research project, you get your data, you calculate your p-value, and then you compare that p-value to the alpha level. Questions there? Normally, the alpha level is kind of set by the region that you're studying in. If you're in the social sciences, for example, you might have alpha level of 5%. If you're in the hard sciences, chemistry, biology, physics, mathematics, that comes much down. Sometimes 1%, sometimes 0.1%. Sometimes alpha level is as low as 0.001%. Right? And sometimes based upon which fields you're in, the size of alpha. The basic rule is if they do not tell you what the value of alpha is, you use alpha as 5%. But if the question says alpha is 1%, then you use 1% as your cutoff number. All right? The basic instructions right here is you assume alpha is 5% unless told otherwise. And almost every time it's going to be a number less than 5%. I don't think I've ever seen anybody go over 5% in quite a while. Very rarely you see a 10% number. Questions there? Questions there? Again, note the p-value right here is kind of saying the probability that the null is true. If you have a p-value of 6%, we're still sticking with the null. Okay? You have to have strong evidence before we switch to the alternative hypothesis. All right, so we run our test. Our they want us to practice deciding whether or not our statement is statistically significant. And so let's say the p-value is 0.0112 right here, and my alpha level is 5%. Do I reject the null hypothesis? Somebody help me out here. Do I reject the null hypothesis? Now is a good time to raise your hand. Okay. Come on, yes. You reject the null hypothesis. This number is small. This is basically saying that there's a 1% chance probability that null is true, yes? My cutoff is 5%. So therefore, we're going to reject the null hypothesis. Questions there? Example number 2. Suppose the p-value is 0.012%, but the alpha level was set at 1%. Do we reject or do we fail to reject the null? I have an answer on the board. She says we fail to reject the null. Anybody agrees or disagrees? Agrees? Agrees? You are correct. We fail to reject the null because this is greater than 1%. A little bit, but it's still greater. Yes? Imagine you're working this for like 6 months and, and you get so close. I can't publish the paper. Questions? Yeah, normally though, since you're so close, you keep working. That most likely you just missed something. You keep working and trying to figure it out. All right. The mean height of adult men in the United States is 69.7 inches, with a standard deviation of 3 points. A sociologist believes that taller men are more likely to be promoted to positions of leadership. So the mean height for male business executives may be greater than the mean height of the entire male population. Interesting. A random sample of 100 male business executives has a mean height of 69.9 inches. Again, compare that against the average. Yes, it's higher. Yes. Assume that the standard deviation for male executives is, again, standard deviation of 3 inches. Can we conclude that male business executives are taller on the average than the general male population at the 05 level? Now, one of the big things about this section is just too many words. So let's kind of parse through this thing right here. So what's the mean height for men? 69.7 inches. What's the standard deviation for heights of men? They gave it to us twice. They're so nice. They're so nice to us. Yes? Yes? How many people were sampled? 100. And what was the average of the 100 people that was sampled? 69.9. All right. Now, with all of that in mind right here, what are we trying to figure out? Male executives, can we conclude that they are taller? Yes? That's what we're trying to conclude. Yes? Yes? So, can anybody give me the null and the alternative hypotheses? Somebody give me the null and alternative hypotheses?
The null hypothesis is
69.7. And then what's the alternative hypothesis?
is
Greater than. Oh, did you remember the adage that these two numbers are always the same? Did you remember that? Yes. So that's our null and that is our alternate hypothesis. Questions there? Again, the 69.9 right here, this is evidence. This came from the 100 people, yes? This number can always change. If I had sampled 200 people, this number would have been different, yes? So this right here is our evidence. 100 people, we took the average of the 100 people, and that gives us our evidence. Questions there? Questions there? All right, so with this in mind, we can go in to solve and then go ahead and figure these things out right here. So first things first, what are we going to put for the mean in salt? 69.7, that's right. What are we going to put for the standard deviation in salt? Not the 3, it's the 3 divided by square root of 100. So it's going to be 3 divided by the square root of 100. So that's going to be 0.3. Yes? Yes? Is this a right-tailed test or a left-tailed test? This is a right-tailed test. Yes? How do I know it's a right-tailed test? Because it is greater than. Yes? And then last one, what I put in the X box, what number goes into the X box? Oh, you guys have no idea what I mean? Let me go back over here. Where did it go? My good buddy Salt. Let's go back to my good buddy Salt. All right, so the X box is what comes inside here. So let's go back to the top. What's the mean? 69.7. What's this? Yeah, 7. What's the standard deviation? 0.3. Yes. It is a right-tailed, left-tailed test. It is a right-tailed test. And then what comes over here in this box right here? 69.9. That's what comes into this box right here. Yes? And these two numbers are important. This number is called it's the probability, but in this section we call it the p-value, yes? And this number down here is your TS, your test statistic. All right? Questions there? Comments? Queries? Concerns? All right, cool. And so 25%. Remember what the alpha level was 5%, right? Do we reject the null or do we fail to reject the null if the p-value is 25%? The cutoff is 5%, yes? So the p-value should have been less than 5%. Is this less than 5%? And so we fail to reject the null. We fail to reject the null. Questions there? All right, cool. Let's see if they agree with us. So the null and alternate hypothesis equals 69.7. It's a right tail test, so mu is greater than 69.7. We calculate the test statistic. Again, they're doing it by hand, but we got 0.667. Because they rounded 2 decimal places, but this is how they got the test statistic. And then a p-value right here. Again, Salt gave it to us right here as 25%. Again, so now we can make the decision. Our cutoff level was 5%, but so we failed to reject the null. The number had to be smaller than 5% to reject the null. Questions there? Again, this is quite clear, right? So this is quite clear, yes. But even if this was, say, 6% or 5.5%, we would still fail to reject the null. Okay. And so our conclusion is there is insufficient evidence at the O5 level to conclude that male executives have a greater mean height than the adult males in general. Questions there? Comments, queries, concern? Okay, cool. So that's the p-value method. How much time do we have? Oh, we got 8 minutes. I was gonna let you guys try this one. We got 8 minutes. Go ahead and try this one right here. See if you can, alpha level is 5%. See if you can use salt to figure out whether or not we're going to reject the null or not. At a large company, the attitudes of workers are regularly measured when standardized tests. The scores on the test range from 0 to 100, with higher scores indicating greater satisfaction with their job. The mean score overall of the company's employees was 74, with a standard deviation of 8%. Some time ago, the company adopted a policy of telecommuting. Under this policy, workers could spend 1 day per week working from home. After the policy had been in place for some time, the random sample of 80 workers was given and the test to see where the mean level of satisfaction has changed. And since the policy was put in effect, the sample mean for those 80 people is 76 points. Assume the standard deviation is 8. Can we conclude that the mean level of satisfaction is different since the policy change at the 05 level? Do we have time to finish? Go ahead and try. Go ahead and try. Go ahead and try. Okay, let me give you guys a head start. What is the null on alternate hypotheses? What's the null on alternate hypotheses? What's the null on alternate hypothesis? Mu is equal to 74, and the standard deviation and the alternate hypothesis is not equal to 74. All right. I don't have enough time. We'll stop here and then we'll come back. We'll finish this last time.